This tutorial deals with common contour binning in OpendTect. Common contour binning, or CCB for short, is a new commercial plugin in OpendTect version 3.2. The ideas behind CCB originate with Jan Gabe van der Weijden and Andries Wever of Wintershall Noordzee BV. DGB developed a CCB plugin on behalf of Wintershall, who are the IP holders and who granted DGB the right to commercialize the technology. CCB is used to detect subtle hydrocarbon-related seismic anomalies and to pinpoint gas-water, gas-oil and oil-water contacts. CCB uses the power of stacking to enhance such anomalies. Consider a structure filled with hydrocarbons. All traces that penetrate the reservoir at the same depth will in principle have the same hydrocarbon column length. In other words, for these traces, the imprint of any hydrocarbon-related effect on the seismic response should be similar. Such traces are located along the same depth contour line. So if we stack all traces along the same contour line, we can expect the hydrocarbon effect to stack up, while stratigraphic variations and random noise will be cancelled out. The CCB plugin produces two outputs. First, a CCB volume is produced that consists of traces stacked along contour lines that are redistributed along the same contour lines. In other words, all traces along one contour line consist of identical traces that were produced by stacking all traces along that contour line. The second output is the CCB stack. This is a 2D section with stacked traces flattened along the mapped reference horizon. Let us now look at a CCB example. At top reservoir level, a gentle anticlinal structure exists. The seismic amplitude map at this level does not reveal an anomaly. Here we have visualized all seismic traces along two separate contour lines. These traces will be stacked per contour line, and the stacked traces are then redistributed along the same contour lines to produce the CCB volume. In this display we see the result after stacking and redistribution. The slight variations along the same contour line are caused by OpendTect's way of displaying random lines by projecting the traces of the nearest grid points to the actual line position. Note that only the traces inside the user-defined polygon are stacked. From the CCB volume we generate another seismic amplitude map. This time we do see an amplitude effect that is likely caused by a hydrocarbon fill. At the crest of the structure we see a small area with reduced amplitudes. Further down dip we observe another amplitude increase. This one coincides with the expected spill point, as we will see later in this presentation. Let us first look at the CCB stack. Consider this to be a seismic section flattened on the reference horizon, in this case flattened on top reservoir. The top of the structure is on the left hand side. If we go to the right, we go down dip. If we look at the amplitudes around top reservoir, we see 2 times a step change in amplitudes. The first step change is interpreted as the gas-oil contact, the second one is the oil-water contact. Now let us finish this interpretation by taking fluid migration paths into account. This display shows seismic chimneys above top reservoir level. We observe that there are no chimneys immediately above the structure, indicating a good top seal. The chimneys are associated with a fault trend to the side of the structure. When we display the CCB anomaly with the chimneys, it is clear that the anomaly and the onset of the chimneys coincide. Based on many case studies, we have come up with a chimney classification scheme that can be used for prospect ranking. The structure we have studied falls in the class we call non-fault sealed trap, which is characterized by the absence of faults and chimneys over the crest of the structure. Such traps are highly prospective. Based on our current statistics, this structure has a 94% chance of finding hydrocarbons in commercial quantities. This concludes this tutorial on common contour binning.